Wigner's friend is another important thought experiment in the foundations of quantum mechanics that hasn't come up on the show really at all. So that might be something worth discussing, or just other things about Wigner
Well,
that.
I mean, let me say a word about the Wigner thing. I mean, the reason I was drawn to Wigner was, I mean, I was a young guy, right? I mean, these are your youthful enthusiasms. I've always thought that the mind-body problem was pretty much insoluble. You can't even, speculatively produce a theory that you'd say, yeah, at least that would solve it. And so if you have this kind of black hole, there's a temptation to take all your other problems and throw it into the black hole and say somehow, the mind-body problem is sitting behind our problems with quantum mechanics and everything else, right? That turns out just to be nonsense, but it was very appealing to me as I literally thought, oh, maybe I can figure a way to do an experiment to figure out whether monkeys are conscious, because if I can tell whether they can collapse wave functions. I mean, and no, seriously, I thought I discussed that with somebody. I can't remember when I was young.
Well, Abner Shimani did experiments like this in the 60s.
Yeah.
So, Abner Shimani worked closely with Wigner. Right.
Yeah.
Right.
You can go off in that direction. Now, the Wigner friend particular example, I always find puzzling because whatever else one would think, you would think everyone would agree that what Wigner's friend does in that situation counts as a measurement and an observation. And so if measurements and observations cause collapses, then everybody should agree there will be a collapse. And if Wigner doesn't put the collapse into his calculations will just be wrong. It'll give him the wrong result. Somehow people, it's this double thinking of, well, I really need these collapses, but I don't really believe in them because I think ultimately, I can just have Schrodinger evolution all the time and it's okay. I think, what's clear is that von Neumann didn't think that. He saw the conflict.
Right.
The fun part is that in the Wigner friend case, it's just bringing out the psychological fact that people were double thinking, right?
We might just set up for listeners who don't know what the Wigner's friend story is. Here's the idea. I forget who is Wigner and who's the friend, but there are two people. There are two observers.
Wigner's the guy on the outside, I think, and the friend is the lab rat.
Okay, good. So Wigner's friend, imagine that there's some electron which is in a superposition initially of being located at point A and being located at point B. Wigner imagines that a friend of his carries out a measurement of the location of that electron. And suppose that we treat that entire measurement interaction, including the brain of the observer, as something that as a circumstance in which the quantum state of the world evolves strictly in accord with the linear deterministic equations of motion. Then the deterministic prediction of those equations will be that once the measurement of the location of the electron has been carried out and has been registered in the position of the pointer on the measuring apparatus, and once the position of that pointer has in turn been registered in the memory cells of the brain of the conscious observer, what the deterministic equations of motion would say is that the observer and the measuring device and the measured electron are in a complicated, entangled superposition, a superposition of one state in which the electron is at point A and the measuring device registers that the electron is at point A, and the observer is aware of the measuring device registering that the electron is at point A, superposed with another state in which the electron is at point B, and the measuring device registers that the electron is at point B, and the brain of the observer registers that the measuring device registers that the electron is at point B. And if Wigner were to look on the evolution of his friend and his friend's measuring device and the electron from the outside, that is, if Wigner were to place the boundary that Bohr was talking about in his quote between that system and himself, to count only himself as the real measuring device here, and to treat the whole system consisting of the electron and his friend's measuring device and his friend's brain as the system that's supposed to be treated quantum mechanically, the system that lies on the far side of the boundary between observer and observed, or between subject and object, or whatever the hell you're supposed to be talking about. If that's how Wigner treated it, Wigner would see his friend evolving in accord with the Schrödinger equation into this complicated superposition. On the other hand, like Tim said, I take it the point is supposed to be that the friend is a conscious agent, okay, must have recorded a determinate outcome to this measurement of the location of the electron, and consequently could not be part of a system which in its entirety is evolving in accord with the linear deterministic equations of motion. So the story sets up a tension, okay? The story sets up a particularly acute kind of tension between what things will look like if you're observing all this from the outside and treating it all as a single quantum mechanical system, and what it's going to look like from the inside. That is, I suppose this could be construed in Wigner's mind as presenting a particularly urgent sort of demand that, as we were talking about with von Neumann, we locate the boundary between those physical circumstances where the linear deterministic equations of motion apply and those where the collapse postulate applies. And this is supposed to set up a tension around that.
I want to. I'm not. It's been a long time since I've read Wigner's paper, so don't take this at all as something to rely on about what Wigner had involved. But there are a couple things I think should be said about the situation. One is that David described it in a way that's not technically quite right. That is, he says, well, if Wigner's the guy on the outside, what will he see this big wave function of the particle plus the detector plus his friend? What will he see that do? And the answer to that, you won't see that do anything. I mean, if you talk about what's observable and measurable, these kinds of quantum states are not observable and measurable. He can't do anything to determine what that quantum state is, not experimentally. It's very important in quantum mechanics that actually you can't do that.
Well, let's see, Tim. I mean, do you mean as a matter of fundamental principle, or
yes,
do you mean as a matter of practical intents and purposes?
No, I mean as a matter of fundamental principle.
So then I'm puzzled.
There is no Hermitian operator whose eigenvalues are all the possible quantum states.
Let's see. I'm not sure I understand. There is
no operator. There is no Hermitian operator whose eigenvalues are all the possible quantum states.
I don't know how all the possible quantum states got into this. The question is
talking about what Wigner will see as the evolution of that wave function.
Oh, no. Okay, good. But let me ask a different question.
Yeah.
Is there a Hermitian operator, okay, of which the state of the particle and the measuring device and the friend at the end of this story is an eigenstate?
Yes, there. I mean, of course, there should be if there's
Right.
no.
And so by measuring that operator, Wigner,
No, because even if there is a collapse, there'll be some chance that he'll get a positive outcome for that measurement.
yeah, you have to do it a lot of times.
You have to do it, and this is the point I'm getting to. This is just a little technical point, right?
Good.
So because it also makes the conflict here an empirical one and not just a philosophical or conceptual.
Right.
That's what I'm trying to get at, right?
Absolutely right.
So for people who know this, and I hope everybody does, or I don't know why you're listening this long, in the standard two-slit kind of experiment, we, as it were, send an electron at this barrier with two slits in it. The quantum state under the Schrödinger evolution evolves so that there's a piece of it that goes through this slit and a piece of it that goes through that slit. And then those evolve together and they come to overlap, and then you get interference bands, right? You get this characteristic bands of very high and then very low wave function. And then if we square that for probabilities, you get these bands, right? You literally see them on the screen. If you do this over and over again, you accumulate these interference effects. If there were a collapse of the wave function right after the slits, so that what survived that was only either this piece or this piece, maybe half the time this piece, half the time that piece, not both, then you would not see those bands. The bands would never form because you would not have the two pieces wouldn't both be there to interfere, right? So if you ask the question, I wonder if there are these collapses right after the screen, you can do an experiment and check. And that experiment will come out one way or another. If there are collapses, it'll come out one way. And if there aren't, it'll come out another. This is not something you just jawbone about, right? Or speculate about. This you can check. And the same thing would be true in the Wigner-Friend case. That is, in principle, although not in practice.
Right.
There'd be a very complicated kind of experiment, and maybe you'd have to do it many, many times on the friend over and over again.
Right.
But if the friend were causing collapses, it would come out this way. And if the friend were not causing collapses, it would come out that way. And so in principle, if you talk about what's in principle observable, or in principle what you can get just kind of concrete data that'll settle, the Wigner-Friend thing should be settleable that way.
Yeah, and I agree with that. And presumably
that really tells you that it's not just kind of optional whether you put the collapses in, or it's just a matter of taste or something like that. No, this has real concrete observable consequences of putting it in.
Yeah, I agree with that, and presumably Wigner would have agreed with that. I'm also not sure exactly where this story comes up in his reasoning through to his final conclusion. But yes, yes, I agree, and Wigner would have agreed. Sure.
I'd like to return to some things that came up just a little bit earlier before we talked about the Wigner's room thought experiment, where, Tim, you mentioned the mind-body problem and experiments with monkeys, and David, you mentioned von Neumann and Abner-Shimoni. And just to put a name to what I think the subtext was going on here, that's the von Neumann-Wigner interpretation.
No, those are different. I mean, at least insofar as I know, those are different. These are von Neumann and Wigner represent two different, in both cases, it seems to me, very clumsy attempts to delineate the location of this boundary that we were talking about before between those physically possible circumstances where the linear dynamical deterministic equations of motion hold sway and those circumstances where the collapse postulate holds sway. Von Neumann is famous for identifying that boundary with measurements, okay? Wigner is famous for identifying the location of that boundary with conscious experience, okay? Or something like that. So both of them are in some sense moves within the same larger program, okay? That is, we've got this Frankenstein monster that we've got to sew together in one way or another, and these are two different speculations about where to put the seams. The trouble is that both speculations, forget about whether they're crazy or anything like that, they're just hopelessly vague, okay? They're not, and this goes back to the remark of Bell's that Tim read at the beginning. They don't involve the kind of language that we have the right to expect in a formulation of a fundamental physical theory.